This is part 8, Vector Embedding of the series, AI for Everyone. Vector embedding is a crucial component of how large language models LLMs function. Since transformer architectures operate on numerical data, they first convert human-readable text into discrete tokens via tokenization. These tokens are then transformed into vector embeddings using an embedding matrix. The transformer processes these embeddings and outputs vectors, which are subsequently mapped back to tokens and detokenized into human-readable text. LLMs operate in an autoregressive manner, predicting the next token based on previously generated ones, recursively feeding their own output as input in a feedback loop that looks similar to RNNs from the outside but totally different in internal implementation. If you've been following this series from the beginning, you might recall our discussion on the engineering mindset, how engineers historically transform characters into different representations such as sound signals, binary numbers, or barcodes to solve various underlying problems. Similarly, in our discussions on neural networks, you may have noticed that data is processed as numerical values, specifically floating point numbers, rather than raw text. This might prompt a natural question. Why are numbers the primary representation inside a large language model, LLM, even though we interact with it using text? This brings us to embeddings, a crucial step in how LLMs process language. Instead of converting each character directly into numbers, which theoretically could be done, engineers found that tokenizing words or subwords provides a more efficient and meaningful representation. However, unlike earlier encoding methods where each character corresponded to a combination of few beeps of sound, as in Morse code, or to a combination of few thin and think lines, as in barcode, or to a combinations of zeros and ones as in binary numbers, embeddings do not map a words to just a few combinations. Instead, they generate high-dimensional vectors with hundreds or even thousands of values per word or subword. For example, 768-dimensional in BERT, 4096-dimensional in GPT-4. Here are the steps to embedding or vectorizations as listed below. Step 1. Let's consider the sentences that you provide as input to LLM like, "The bank is open," or one like, "I deposited money in the bank," or "I walked along the riverbank." Step 2. It converts each word or subword into tokens as shown in the picture. This conversion is deterministic. For word bank, it will always convert it to 3452 as a token. It does not matter where in sentence or in which sentence it is used. Step 3. Next, for each token, it will generate multidimensional vectors. Even though the token for word bank is always the same, for example, 3452, irrespective of which sentence it is used in and where in that sentence it appears, the vectors or embedding will be different based on where it appears within a given statement, as it can be seen in the picture below. These vectors are of floating numbers, and how many of them will be generated will depend on the model being used. Here you may ask why floating point number and not integers. Floating point numbers enable fine-grained updates to model weights during training, which is essential for optimization methods like stochastic gradient descent, SGD. Integer representations would lack the precision required for effective learning. This translates to the ability of model to learn many patterns by slightly updating its numbers, versus if we were using integer values. Also, floating point numbers allows LLMs to find semantically related word using mathematical operations like dot product, also known as matrix multiplications, which is used inside an attention head or a cosine similarity functions used mainly in RAG system. Why so many vectors for one word? Why not few of them, you may ask? A single word does not have a fixed, isolated meaning. It exists in a rich semantic and contextual space. Embeddings aim to capture the diverse attributes and relationships of a word across different contexts. For example, the word light has attributes like brightness, color like blue, green, etc. The word man or a woman can be described with attributes like height, fat, thin, age, color, UNLC, auntie, king, queen, etc. Instead of assigning a single number to a word, embeddings represent words as multidimensional vectors, where different dimensions encode different aspects of meaning. This allows the model to distinguish between different usages of the same word based on the surrounding context. Each dimension captures different aspects of meaning, allowing words with multiple meanings to be positioned differently depending on context. A word apple could mean a fruit, based on the context of the statement it is used, or in company named Apple. In summary, embeddings generate many numerical values per word because language is inherently multifaceted, and capturing these dimensions allows LLMs to understand and process text in a way that reflects human-like comprehension. Here is an example of how word food looks like after converting it into vectors. The diagram only partially shows the list. Here is an online tokenizer from OpenAI. Here you can see in real time how it generates the tokens. You can switch to different models and note down how it changes the token number, even though the text is still the same. Let's now visualize this high-dimensional vector space using the TESNE algorithm. TSNE stands for T-distributed stochastic neighbor embedding. Visualizing data with dimensions as high as 1,500 or 4,000 can be challenging. TSNE, a machine learning algorithm for dimensionality reduction, helps project high-dimensional data into a lower-dimensional space, typically 2D or 3D, while preserving local similarities, making visualization more intuitive. Here you can see the cluster of handwritten numbers in 3D space. Note how the clusters are divided into different colors, each color representing specific digit. Also note how a given number's variation are all in the same cluster. Here is another look into vectorization or embedding of words. For each word, it generates hundreds of vectors, as can be seen in the picture. To summarize, here are the steps again. We input the text, it gets tokenized, then high-dimension vectors are generated for each token.